chair, Mr. Jimin Lai from Sinotech. Professor T.T. Wang, Wang Taidian asked me to, very briefly introduce, Taiwan Session. Actually, in Taiwan Session, we will have 2 parts. The part 1 is called Smart City and Infrastructure, and part 2 is Natural Hazard mitigation. And we too will be in charge of the half part of the part 1, okay? So now we would like to invite the first speaker for the part 1, Dr. Rongfeng Zhang, okay, a very good friend of mine from Moore Associate, okay. Dr. Zhang got his PhD from Cornell, now is PE, Geotech, right? Okay, yeah, please, Dr. Zhang, yeah.
Good afternoon, ladies and gentlemen. Thanks for kind introduction from Benson and Mr. Lai. It will be a great honor to be the first presenter for this session. Today, on behalf of the representative from the Department of Rapid Transit System, we call it DOTS, from Taipei City Government. Mr. Wang, that's the director of the project, first district project office, and another one is Mr. Chang from site office. There's another 2, my colleagues is Dr. Hu and Dr. Zhao. We would like to share with you through a completing MRT project. We will look at the pile construction and loading effect on the adjacent shear tunnels. Today I will just briefly show you the background of the project, followed by the analysis and design. Then we will look into the construction stage and some of the monitoring results. And I will give you the short concluding remarks at the end. The Taipei MRT circular line phase 1 that started from the bottom of the slide shows here. That's a Y6 station, all the way to the north to the end of the station 119 at Wugu district in New Taipei City. The total length is about 35.4 kilometers with about 15 stations. I believe the first 2 stations are underground stations, and for the rest of them are elevated stations. The project we look into will be the design lot DF113. It started from the east side of the Banqiao station all the way to the end of the project. In this specific project, we call it DF113. It's all elevated roads with the total length about 6.4 kilometers and 5 stations. It connects with Blue Line and also Taiwan Railway, Taiwan High-Speed Railway at station 115, and Orange Line at station 117, and the airport link at the end, that's station 119. Through the route, there's somewhere between station 115 and the station 116. There's our alignment somehow overlap with the operating Blue Line for more than 800 meters. So our viaduct will be placed or erected in between the shear tunnels. And this is this specific case is the study that the cases that we will study. The near surface geology is almost overlain by the Holocene aluminum, which is composed of sand clay interbedded layer until you encounter the gravel at a depth of about 50 meters below ground surface. From the pile foundation design point of view, we consider this gravel as a barren strength. So let's look at this study case. Over over 800 meters of overlapping with the operating blue line, there's a total of 20 piers erected between MRT tunnels. And the tunnel dimension was about 5.6 meters for the inner and 6.1 meters for the outer diameters. The overburden varies from 11 to 21.1 meters. That's equivalent to about 1.8 to 3.5 outer diameter of the tunnel. So it's about 60 meters on average. The spacing for this section of the tunnel is ranges from 7 to 9.3 meters, and that's equivalent to 1.1 to 1.5 OD. So here shows you the geometry of our pile foundation and our planned pile foundation and the existing operating shear tunnels. The side groundwater condition is probably the groundwater table is about 2 meters below ground surface with the hydrostatic distribution with depth. And the table on the right show you the design parameter that were adopted, not only for the numerical analysis I will show you later on, but also the design for design purpose. So the depths that the tunnel passed through is probably somewhere around the sublayer 4 and 5, which is clay layer on the top and the sand layer on the bottom. So over these 20 piers, we pick up the specific piers for our study, which is P15-18. The reason to choose this was because the spacing of the tunnel within this section is somewhere around the smallest spacing, which is about 7.4 meters, and also the loading on top of the pile cap is among the greatest over the 20 piers. By looking at this geometry, we start with the 3D numerical model, and here shows you the dimension of the model. It's about 120 meters long and same dimension in width and with 70 meter height. The gravel is somewhere 50 meters below ground surface. I'm not gonna go through the detail of the numerical analysis because you can read the reference in the papers. So I just show you some feature of the analysis. Here shows all the dimensions we simulate. That's tunnel, pile, and the pile cap. And the bottom right shows you the loading. That's ultimate loading applied on top of the pile cap. The following slides will show you some representative results that we obtained during the design stage. The first one on the left is the tunnel deformation induced by pile construction. By the way, because due to such close or limited space between pile and the tunnel, we adopted casing pile method to construct the pile. The way that we did this is to limit the piling effect on the tunnels. So we simulate through the 3D model, and here shows you during the pile construction, it will induce about 0.6 millimeter mesma of the deformation on the tunnels. The result on the right is show you the deformation that induced by the superstructure loading. It will induce with a mesma value of about 2.4 millimeters. And here shows you the induced deformation with respect to the construction step. So with this specific pier, we have 3 piles. So we start with the pile 1, 4, 5, excavation and concreting, and the rest of the 3 piles, excavation, that's in the subsequent procedure, and concreting. At the end of the pile construction, then there's the cap excavation and concreting. At the end, the final stage will be the loading on top of the pile cap. So the result shows you about the total induced deformation is about 1.4 millimeter on the tunnel, and about 32% of the total deformation comes from the pile construction, and additional 4 points was contributed by cap construction, and for the rest, 64 meter of the induced deformation comes from the loading. And when we look at the deformation in the longitudinal direction, here shows you the effective range is about 40 meters. So here's a summary. Here shows you all the results, and we compare with the requirement. Fortunately, we all made the requirements. But in the design stage, after the analysis, we still feel uncomfortable about the piling, so we introduced some low pressure grounding around the pile. That shows you the plan view, and that's a section view. And the contractor proposed a double packer, or we call it TAM, to perform the low pressure grounding. And we also introduced automatic monitoring for shear tunneling. That includes electronic horizontal beam sensor, reflector prints, and total station and convergence point. And here shows you the measurement level, and I'll just point out that the alert level is about 80% of the action level. The following slides will show you some monitoring results. As you can see that either from the beam sensor or the refractor prints, they all show you very limited deformation obtained. It's somewhere, they fall somewhere around 1 millimeter. That compared with our measurement level is quite satisfactory. And for the convergence point, it's somehow larger, but it's still falling the range about 3 millimeter. And here shows you it's probably still within the 10 millimeter compared with our other level, which is about 16 millimeter. Then I'll show you some construction photos taken on the site. Here is the low pressure grouting. That's the casing pile I just pointed out. Here's the casing, and that's the grab, and we locally call it a shock head grab. And here is the pile cap construction, and we introduced pressing rig with low vibration and noise. Sorry, I'll just go through the last one. And through this project, and we'll see that the proximity effect become a feature in our MRT project. And for such complicated soil substructure interaction, it will be easy way to introduce numerical model. And the result can be applied to the design and the construction stage. But at the end, as an engineer, you got to feel you need to get some feedback from your design and also construction in the way that you can enhance your engineering judgment. And that's probably the most important way you execute a project. And that's the end of my presentation. Thanks.
Thank you, Dr. Zhang. And Dr. Zhang is also my senior brother in the National Cheng Kung University. And the next two, we will, from the Taipei MRT, move to the Taichung MRT. And we will talk about the challenge of deep excavation, dewatering, and the semicircular pie in gravel formation. And the speaker is Dr. Junxin Yan. And I graduated from the National Zhongxin University. He has worked in the CCI 11 years. It's very, have a lot of the experience in the Taichung area. And the Taichung area is a lot of the gravel formation. And welcome the Dr. Yan.
Hello. Good afternoon, ladies and gentlemen. Thank you for being here to attending Taiwan Session. I am Yan Junxin. Okay, it is my honor to be the representative of Taipei City Government, the Department of Rapid Transit System. And today, I'm here to introduce you the challenge in Taichung, about the deep excavation, dewatering, and the semicircular pie. And today I will divide my presentation for 4 parts. Okay, and I will begin with the introduction about Taichung MRT system. And maybe some of you, this is the first time to come to Taiwan, so you have to know where Taichung is. We are in Taipei right now, right? And Taichung is here. It is located in central Taiwan. And the Taichung MRT green line, this line is the first line in Taichung. And in this line will be complete and the operation in the end of next year. And they have 18 stations. And for our project, they have 6 joint development stations in our project. And the joint development, in this project, we only construct the transportation space for public use. Okay, in the future, Taichung City Government will put further investment out to tender. Maybe it is residential or business building. Okay, and for our joint development station in Taichung City, okay, all all the depths of excavation are less than 27 meter. And I leave a blank here at G91. Do you want to guess how deep is? The answer is the answer is 36.75 meters. Very, very deep. You can imagine that almost a 12-floor building in underground. And let's talk about the deep excavation. And before we talk about excavation, we have to know the geological condition first. In Taichung, it is gravel formation. And from 0 to 5 meter below surface, it is backfill and salty sand. Below 5 meters, it is gravel and a lot of gravel and boulders. The biggest boulder we found in job site, it is bigger than 1 meter. And let's talk about the groundwater table. From 2007 to 2013, the underground table was 12 meters below the surface, very stable. But until 2016, the groundwater table was raised to 6 meters from surface, a very huge difference. And in this next, we will talk about the G91 station. This is the distribution of retaining pile in G91. Totally, we have so many pile and king post. And this is the area photo for job site. And the excavation procedure of G91, first of all, we have to construct a lot of pile and king post. And the excavation and the structuring installation. And we also use a lot of planing rebar and wire mesh to be the reinforced material. And at last, we will use shotcrete to cover it, to cover the gap between two piles. And if the excavation process was too fast, we sometimes the following construction cannot catch up. We will leave the gravel, the soil as the day load to prevent the gap become loose or decompression. And during the excavation, we also find a sand layer in our job site. This is the sand layer. The permeability of this layer was much lower than gravel formation. It is make a lot of problem for us to dewatering, yes. And this is the original distribution of our pumping wells in G91. Totally, we have 22 pumping wells, and because the groundwater table was raised, and because the fine sand layer, it makes the dewatering become more and more complicated. And the final distribution of the pumping well is increased from 22 to 47 because we have to keep the groundwater table lower than our excavation surface, yeah, for the safety, right? So we have to add more and more pumping wells. And even we monitor the groundwater table. The water table from observation well is lower than our excavation surface, but they still have a lot of water, the seepage, flowing out from all around in our job site. And if the water keep flowing out, we cannot use shotcrete to cover our gap, right? So we use the metal plan and use the gravel as the day load as the form. And we pouring concrete directly, okay, to displace the shotcrete. And if they still have a lot of water flowing out, we will dig a ditch for drain water to keep the surface was dry. And if some water keep flowing out from the vertical surface, we will install some PVC tube to drain the water to the nearest pumping well. And let's talk about the semicircular pipe. And semicircular pipe was used in G92. Okay, semicircular pipe, they have 1004 semicircular pipe in G92. And this is the aerial photo in job site. And let's talk about the procedure. First of all, we have to fabricate the rebar cage, right? But the most special is it is semicircular one. And for this side, the rebar is only for the support because you have to install the rebar cage into a casing. So we also use the high density foam to fill the gap. This one, the white one, because they will have some gap between the rebar cage and the casing. So we have to fill it. And the fixed end of the cage was circular. And as the full casing pipe, we have to draw in, and we have to install rebar cage. And because the pipe is very long, so we have to lap and slip one time. And because it is semicircular pipe, means the install instead of concrete side, we have to screen in gravel and refill it. Okay, so we need to prepare a funnel for the gravel backside, and we pour concrete and gravel backfill in the other side, and we will extract the casing, and this is the semicircular pipe when finished. This side is for gravel, and this side is for concrete. In the beginning, you can see the process is very complicated. So in the beginning, we have to 30 hours to finish one per pie, okay? But after discussion and improvement, we can finish one pie in 20 to 25 hours. And let's use animation to introduce the process. First, we install the casing, and we install the rebar cage, and we pour in concrete and pull out the case, and we pouring concrete again, and gravel refill. Okay, and repeat to finish. Okay, we finish one semicircular pipe, and we use the tie beam. We use the tie beam to connect all the pipe together, and we will excavate it from top to bottom. And the discrepancy of two methods. What difference between full casing pipe and semicircular pipe? And this one is for semicircular pipe. You can see it is when you finish, it have a curve, okay? And the semicircular pipe, it will be finished with a plane surface. And what difference? If we build a full casing pipe, we have to build the basement wall here, align the pipe, right? And but if we construct semicircular pipe, we can have an extra 7.5 meter space. Okay, what different? If we have a job site with 50 and 50 meters, on the left side we use full casing pipe, and on the right side we use semicircular pipe, and we can build the basement wall on different place. Okay, this wall is the thickness of the wall is 0.6 meter, and what the difference is the internal area. If we use semicircular pipe, we can have extra 140 meters for each floor. And finally, we come to the conclusion. And the challenge of the deep excavation, the gravel formation for us, it is very because the hard hard gravel and boulder, it makes it is hard to drill deeps. And we still have a lot of problem about the groundwater and the seepage. And the challenge of semicircular pipe is the balance and noise. What means the balance? We talk about we have to pouring concrete and gravel backfill, but you cannot pouring concrete too much. You cannot pouring concrete in one time. You have to make a lot of steps, because if you pouring concrete too much, the rebar cage will be a little bit tilted. Okay, and it will be stuck the casing, and the casing cannot pull out. And the noise is because we have to refill the gravel, yeah. And you can imagine that when we refill the gravel, it make a lot of noise, extremely noise. So in the beginning, we can our neighborhood live in the next building. They always throw something to say hello to us. Stop doing that. Okay, and all that we can do is adjust the construction time. We adjust the time to the room. Make sure everybody is awake. Okay, and the last challenge is we have to alignment, because if you this is semicircular pipe. If the line is not in the same line, we have to demolish it when we construct the wall. Okay, if the line is not right, you have to demolish the pipe. And the benefit of semicircular pipe, because we use less concrete. Okay, so we can reduce carbon emission. For G92 station, we can save 462 tons CO2 emission. And because we save a lot of concrete, so we save the budget. For G92, we can save 7.3 million new Taiwan dollars. The most important thing is we increase a lot of space. For G92, we can increase 228 square meter for each floor. And in G92, there are five basement floors, so totally they can increase extra 1,140 square meters. Okay, just in time, 15 minutes. Thank you for your listening. Thank you.
Thank you, Dr. Yan. Let us give him a big hand again. And after two speakers, we have the 15 minutes question and answer. If you have Taipei MRT question, you can ask Dr. Zhang. If you have the Taichung MRT question, you can ask the Dr. Yan. And any audience have any problem?
I saw that if you have a question about the clay, and send you as Dr. Zhang, and gravel you as Dr. Yan. So is there any questions? Yeah, please.
Hi, this is Ming Cai from CTCI, and I would like to ask Dr. Yan, right? How is the spacing of the semicircular pile? And yes, spacing. No spacing.
Center to center
Yeah,
spacing.
yes. Yes.
3 meters, because the diameter is 1.5 meters.
So they are not overlap.
Not overlap. You can see the gap. Yeah,
Okay.
you
So-
can see the gap. You can see the gap
yes.
between two piles. We use wire mesh and planing rebar as the reinforced material, and we use shotcrete to cover it.
Okay. So and how do you think about the water problem? Actually, I have involved one of the Taichung MRT project. I remember it's maybe G90. I don't remember because I have calculated the dewatering for the for CEC dewatering. When that time I was in the CEC, so I have calculated dewatering, and we encountered one problem in construction site, which is we found that the groundwater level is not so high, but after when we start the watering work, but the water start pouring into the excavation hole, and we just can't stop. Just the water is the flow is very huge. So we're still not sure why this problem occurs. So I wonder if you have any comment about this situation. Thank you.
Okay, thank you for your question. That is why we increase so many pumping wells to this job site from 22 to 47. But even though we cannot stop the water flowing out, right? So we have to do something. We just pumping water out. We cannot stop it. The water is too much. You never can stop it. The most important thing is you have to drain it, to pumping it out from your job site. You can see we dig a lot of ditches around our job site in order to drain the water to the nearest pumping well. And we also install a lot of tube on the vertical surface. Okay, we cannot stop the water flowing out. We just pump it out. Do
you know where is the water come from?
From the sky or from underground. Yes, I have no idea. But all that you can see when we observe the water table from the observation well, it is very lower. But we don't know why water keep flowing out. Maybe it have some. I think it have some seepage on some special place. I don't know where is the water coming from. If I know that, maybe I'm the god. Yes. So sorry. We don't have the method. I think we cannot against to the nature. We cannot stop the groundwater. We just pump it out. Yeah, that's my answers.
Yeah, maybe for this, we have some ideas, I guess. Yeah. First of all, I think the void ratio for the gravel in Taichung is quite high, so that's the reason why permeability is high. Okay, so water easy to come in, and the thickness of the gravel in Taichung is also very thick. And again, the gravel go everywhere. They will go. That's extend to. You never know. Several kilometers or something like that. So water, once you have a larger scale pumping, right? Like Jimmy, once you have a larger scale pumping, and then the water will all come to the same place. You have any further comments?
I think the CEC is a lot of the experience about this because CEC is a construction contractor. So it's a very difficult problem because in Taichung, maybe some place the water level is high, but the dewatering is the challenge. But some place the water level is lower than another place. So the sixth place maybe have the sixth condition.
Is there any other question? Jimmy, you want to ask?
No. I think you also can use the Chinese because the Benson can translate to English.
Why me, not you? Okay.
So have any another problem?
Yeah, you can ask in Chinese. That's fine. Even though Tina asked me to shut up.
If anyone have question, I will stay here in the next 3 hours. I will be here. So if you have any question, you can find me.
Oh, okay, I think be a chair. The other function. Is to ask the question, right? Okay. I think I have one question for Dr. Yan. Okay, can you go back to the photo you show us the semi, what you call the semi casing pile? You have a cross sections, show half concrete, half gravel.
This one?
Yes, yeah. We just curiosity. Okay, why in the gravel side you still have a rebar there? How can you put them in? But how can you put them in?
Oh, why we still need rebar here? So it is because we need to the rebar cage for only for support, for support. Because if you don't have rebar here, it will be tilt, and it will stop tilt because you only have semicircular. If you don't have the rebar here for the support on the casing, the tire the rebar cage will yeah. So
how you put it?
how to put in the same as the just like this we put in install the rebar cage, and after when we excavation we will cut the rebar. We will cut the rebar out. We will remove it. Okay, we only leave the in the this part the rebar will be removed when we excavate. And after
Because in this you didn't plug any rebar here.
yeah, because we have to remove it. Because we have to remove it. But if you dig deeper, you can see the rebar underground here. And this surface, we have to remove the rebar. Yeah.
Okay, so basically, you need to, remain
Yeah.
the rebar gauge is vertical.
Yes, yes.
Okay. Any question from you?
I have one question asked Dr. Zhang. And you use the Midas to analyze the shear tunnel in the operational. And have you been used the prices 3D and compare with the Midas? And if you have any experience, can.
First of all, we didn't check with each other in the private about this question. So, second of all, no, because we have no chance to apply process 3D. And actually, back to that time.
With us, we have a 10 user.
Okay.
Process 3D.
We bought one, and we can operate by ourselves. Actually, back to that time, process 3D haven't come to the market yet. So the only choice we can pick up is the Midas. We haven't got a chance to compare the result.
Okay.
But actually, if I have time, we do perform the excavation right next to the study case here. It's station Y15. But I didn't show you here. Okay. We did use Practice 3D to perform the excavation on the station 115. Because there's also a special case I presented in the last Southeast Asia conference last year. The one that's also encountered the MRT line and also Taiwan Railway and Taiwan High-Speed Rail on the other side of the excavation. Yeah, that's another special case. But for this, for our cases here on the Wenhua Road, we didn't. Yep.
Okay, now the project is finishing now.
Yep.
And do you compare with the field monitor data and the analysis data?
Yes, we did. Here shows you the numerical result. That's the represent a typical result. We didn't have time to, analyze it peer by peer. We just choose the most critical one as a typical. Here is the monitoring result. All four win the management level. So that's somewhere that our other level is around, 9.6 millimeter, and action level is 12 millimeter. But the monitoring result is somewhere around 0 to 1 millimeter. That's for the beam sensor. And the other one is a refractor prints with total station. But this is that's a comparison with the our result from beam sensor, and they kind of will well compare with each other quite satisfactory. And the last one will be a convergence point, and here it shows you that's the ratio deformation for each tunnel section. And here is the yeah, I forgot to mention because time limit. Yes, it just happened that for this specific pier, the contractor planned the construction within the same month. Is August of 2015, and the first 2 weeks of the August they perform low pressure ground improvements, and the final 2 weeks they start piling of this specific pier, and you show you within the whole month the variation of the data that still fall into somewhere around that's 5 millimeter, and here is just around 8 millimeter when during the construction of low pressure and piling. Yep, that's about it.
Maybe I just follow. Okay, the last two questions. Okay, I think probably you use constitutive models for more coolant, right?
Yep.
Yeah. So it means now we use a more advanced model. Seems not very useful. In this case, because looks like if you say, this one is suitable, then we just choose more coolant is enough.
Actually, from the point of design engineer, we try to design our target not too over conservative, but still within the conservative side. I forgot to mention.
That's why you say.
Yeah. Even we did a series of numerical analysis that cost a lot of time and money, but we still at the end of the analysis, we still don't feel comfortable about the analysis. That's why we during the design stage we plan the low pressure grouting that circulate the pile, and also 1 diameter above and below the depth of the tunnels. Yeah, that's to safeguard the tunnel, well, to be on the safe side but not too conservative. Yep.
Okay, because already they show me the time up, so we have to close the sessions. But before we close, this half sessions, we on behalf of the conference, we need to present our gift to our speakers. So first, Jamie, you give a gift to Dr. Yan, please. Yeah. Yeah, can we have some help from the crowd? Yeah. Okay, next one. Hey, Jamie, all your time. Or, okay.
Change to you. That Dr. Benson gave to the Dr. Zhang. So we finish my part. And yeah. Hope you enjoy it. Then we'll change to the Dr. Zheng and the manager Zhou. Thank you, everybody.
Thank you.
Okay. Good afternoon, everyone. I'm Zheng Shihao from Taiwan Tech. He is Zhou Kunxian from CCI. And we are going to chair the next two presentations. The next two presentations are from Public Works Department, Taipei City Government. And the first presentation will be presented by Ms. Liu Zhongxiu. And her topic is the build achievement of the intermediate soil liquefaction potential map and the inequality system of Taipei City. Okay.
Ladies and gentlemen, I'm the engineer of the Public Works Department, Taipei City Government, Liu Zhongxiu. I'm glad to have this opportunity to be here. Today's speech is the build achievement of the intermediate soil liquefaction potential map and the inquiry system of Taipei City. Today's speech outline is divided into the origin of the project, the process of creating the soil liquefaction potential map, the application of the inquiry system, the conclusion and the suggestions. First of all, what's liquefaction? In the case of saturated, loose sandy soil and the high groundwater level, if a large seismic is encountered, the moisture between the underground sand particle may be squeezed out. The sand becomes a liquid in the water, which losing support and causing ground facility to fall and break. This is the type of disaster caused by soil liquefaction include surface water spraying and sand blasting, and the manhole and the pipeline to fall upward. Building structure subsidence, earth impairment damage, etc. A total of 18 soil liquefaction events occurred in Taiwan from 1816 to 2016. The soil liquefaction problem is serious in Taiwan. Taipei City is located at the northern end of Taiwan. It is about 27 kilometers long from north to south, about 20 kilometers wide from east to west, with an area of 271.8 square kilometers. It has a population about 2.7 million and divided into 12 districts. Except for the surrounding area of the Danshui River in the west of Taipei, the rest of the city is surrounded by mountains and belongs to the basin topography. About 55% are hillside area, and there is no possibility of soil liquefaction. Therefore, the project is based on the basin area, about 120 square kilometers of the analysis range. The range marked by the line in the map. After the GG earthquake in Nantou on September 21, 1999, early city government began to concern the problem of soil liquefaction. The Taipei city government released the first version of the soil liquefaction obtention map in 2002. After the Meinong earthquake in 2016, the central government released the primary map in March of that year. Then the Taipei City government released the middle level map in September 2016. After that, Taipei City government continued to improve the middle level map in March 2018 and released the advanced version of the middle level map. Today's speech is to describe the process of creating the advanced map. First of all, the project had established the process of creating the soil liquefaction potential map. The existing drilling data was collected, screened, and corrected, and then the additional drilling was performed on the area where the drilling data was insufficient. Then various methods for analysis were compared to develop the soil liquefaction analysis system to map the middle level potential, and then created a computer search engine for the public and the professional to search the relevant information online. This project collects total 14,031 holes of the drilling data from the Central Geological Survey, the Mass Rapid Train Project, the Taipei City Government Public Works, etc. After analyzing and screening the collected drilling data, we would drill additional holes in the insufficient drilling data area to achieve at least 4 drilling data per square kilometer for analysis. A total of 119 holes were drilled, 30 meters deep per hole in principle. The drilled holes were distributed in 12 districts of Taipei. In this project, from the 190 additional drilling holes, 30 self-metering and 150 artificial water level observation wells were selected to obtain data for analysis. The self-metering water level observation well were recorded once per minute, and the artificial water level observation well were observed every 2 weeks for the long-term water level observation in order to get the accurate groundwater level data in the Taipei Basin. The left picture shows the observation well distribution map. The picture on the right is the groundwater level depth map. And this project will collect more than 14,000 pieces of the drilling data. According to the coordinates, location, depth, SPTN, unit weight, unified soil classification, and the other items to analyze and screen. We finally select 4,769 pieces of the drilling data, except for the Guandu Plain. Guandu Plain is here, okay. And the Beito area, the select data could meet the principle of 4 holes per square kilometer. The drilling hole distribute map is shown on the left picture, and the right picture shows the distributed density of drilling holes. The deeper color area means the higher distributed density of the drilling holes. After collecting the drilling data, we follow the procedure of establish the soil liquefaction potential map to calculate the liquefaction potential index. According to the engineering geological characteristic in Taipei, we analyze the soil liquefaction potential index between the drilling holes by Quincke interpolation method. Then we check whether the data was reasonable and repeat the relevant step until the result meets the requirement. Then we invited relevant experts to guide and review. Finally, we release the map. The liquefaction potential analysis uses the hyperbolic function method recommended by the central government. The safety factor is equal to the ratio between cyclic resistance ratio and the cyclic stress ratio. The liquefaction occurs when the safety factor is less than 1. And this is the design parameters. The acceleration is 0.24, and the seismic intensity is 5, and the magnitude scale is 7.3. This project did not only select the hyperbolic function method for analysis, but also select different analysis to verify and compare. And this is the analysis of the liquefaction potential map. The high potential area shown in red is 22.58% of the project area. It's 9.97% of the total area of Taipei. It's mainly distributed Datong district, Datong and the Zhongshan district, and the Shezi Island, and some area of Zhongshan district are located along the Danshui River. The middle potential area shown in yellow is 14.58%. It's 19.68% of the total area of Taipei. It's mainly distributed south of Songshan district and the Nangang district along the Keelung River. A low potential area shown in green, and is 32.84%. It's 14.5% of the total area of Taipei. Okay. After completing the soil liquefaction of potential map, the provided will establish in an inquiry system to provide public or professional to search it online. The website is soil.taipei. The website content includes the past and present of the Taipei Basin, about the soil liquefaction, investigation and the mapping, potential map search, map download, and the soil liquefaction question and the answer. The project established the website, which did not only provide the related information of the soil liquefaction for public to search and download online, but also produced question and answer, videos, and the animation for watching online. It would let public understand the content of the soil liquefaction, the disaster prevention plan, and the policy of the government in order to reduce the public concern and the fear. In addition, this website can also provide professionals to search the name, number, coordinated, groundwater level, depth, liquefaction, analysis index, etc. of the additional drilling holes and provide liquefaction analysis report and the 3-dimension histogram search function. After completing of the soil liquefaction potential map, several departments of the Taipei City government currently have several value-added applications, include to develop the disaster response routes in high potential areas in order to maintain the traffic for emergency relief when the earthquake comes in. To provide the building block ratio bonus for urban renewal case if the developer improves the site foundation in high potential areas in order to accelerate the old house to rebuild and improve the safety of residents. To change the anti-seismic joint of water pipe in high potential areas in order to keep the water supply during the earthquake. Finally, the conclusion and the suggestion of this project follow. This potential map can be applied for decision making in urban disaster planning, urban planning, etc. The actual drilling holes are 4,769 holes with an average of more than 4 holes per square kilometer for the liquefaction analysis. It has the highest density in the city where the map has been released. The project currently collects the drilling data of the building construction case for analysis in order to continuously improve the accuracy of the map. This is my speech. Thanks for your attention.
Good afternoon, ladies and gentlemen. I'm Kun Xianzhou from CECI. I'm very glad to introduce Mr. Si Yuan Lin. Mr. Lin got Master of Geotechnical Engineer in National Taiwan University in 2002 and MBA in Iowa State University at 2019. Taipei City here has about 400 geological sensitive landslides and more than 34,000 man-made slopes. Geological Engineer Office, GEO, of Taipei City government has built automatic system for monitoring, feedback, and warning of the slope land. Let's welcome Mr. Lin.
Thank you, Mr. Zhou. Ladies and gentlemen, good afternoon. My name is Si Yuan Lin. I work in the Taipei City government, and my organization, Geotechnical Engineering Office, is responsible for the safety, disaster mitigation, and management of the slope land. Today, I'm here to introduce you the evolution and prospect of the digital management in slope land. First, I will introduce you who we are and what we are doing, and next, I will talk about the digital monitoring system that we are using now and how we apply the digital instruments and digital technology in our work and our prospect. So let's talk about ourselves. There are more than 15 acres slope land in Taipei City, which is more than 55% of the Taipei City. More than half is quite beyond many people's recognition, including myself. So my organization, the Geotechnical Engineering Office, is trying to provide a safety and recreational environment for the people who live in Taipei. Our major tasks can be divided in 3 aspects: the management, the disaster prevention, and the utilization. For the management, we examine and inspect the soil and water construction plan to make sure every construction is following the law, following the regulation. And also, we conduct the Forest Act to ensure a healthy forest in Taipei. For the disaster prevention, we put our focus on the maintenance and improvement of the slopeland, and also we hold the patrol and monitor work for the potential risky area, and also we hold the disaster prevention education for the people to boost the knowledge of the disaster prevention, and moreover, we execute the excavation drill for the people who live in the slope land to teach them how to escape, how to mitigate the disaster, and how will they do when the disaster happened. For the utilization, we maintain the mountainous roads, hiking trails, and the scenic zones and the campgrounds to provide a recreational environment for the people. And also, we hold the environmental education for the people who want to know more about the environmental knowledge in the slope area. So to be specific, these are the major tasks that we hold in our organization. Moreover, we supervise all the soil and water construction projects in Taipei to make sure not only the public work, but also the private sector can follow the regulation. In 2019, we completed the limits on its permitted scope of use, which is the regulation of the land use. And also in the same year, we started the Taipei Grand Trail project. It is the most famous hiking trail in Taiwan. Its total length is reaching to about 92 kilometers. And I really encourage you everyone to try this hiking trail. It is very cool, but very challenging, yes. But you don't need to worry about that. They have lots of exits and entrance, so you can split this challenge for several days. All right, like I said, our most important work is to manage the slopeland. How we do that? The most important emerging progress for the management is our smart management system. It is the soil and water conservation plan database to provide for the electrolyzation, online application, and approval. It is also an illegal cases database, which will generate the audit notice for those historical illegal cases to make sure they do not break the law again. And also, it improved our inspection efficiency by the use of online form or the mapping platform. These are the characteristics and the functions of the smart management system. From this smart system, we can get the basic information for every construction project. It allows us to use the online application and approval. It provides information for analysis and decision support. We use it to check the examining history to make sure every work is on the track. And also, we manage the present or upcoming construction site to follow the progress of the construction. And it also provided information about the facility maintenance. Since everyone is online and integrated in this system, it will automatically generate the basic information for online review. And also, we can track the case progress, and we can assign the user access authority by the case status, like it is in the review status or construction status or the maintenance status. And everything is online, so we can upload and forward documents to relevant committee to review and approval. Because of the digital communication, we don't have the paperwork right now, and these do not save the paper, but also it shortens the review duration from the 7 months to 3 months. It's quite increased the efficiency of the review. The second part is the digital monitoring, including the multi-scale monitoring and geological sensitive areas and man-made slopes. In addition to the approved construction, there are unapproved developments in Taipei City, which are illegal cases. To find out and deter these cases is very important but very tough, because there is more than 55% slope land in Taipei City. So we devised a multi-scale monitoring procedure to overcome this problem. It is a composite monitoring mechanism, including the satellite image, which is the broadest view, and the aerial photo, which will provide a more detailed overlook in Taipei City. And from the satellite image and aerial photo, when we find something is unusual, we will use the UAV and the ground patrol to audit on site. And I think from this multi-scale monitoring, I think we can capture every activity, including the approved or illegal activity in our slope land. The UAV can not only apply in the illegal cases, we can also use it apply in the approved construction. We use the UAV to generate the 2D or 3D model of terrain and construction, the buildings. And we overlap the engineering drawings to find is there, to avoid the visual blind spot where maybe we may not, it's harder to reach. And also we can monitor the construction progress, and we use this to assure our construction quality. This is a case. This is a park in Beito. And this is 2D model, and this is 3D model. In May, we can see the drainage ditch. This facility is 5 meters offset to the place where it should be. So when we find this problem, this mistake, we ask the constructor to amend. And in August, then we can see the drainage is on the place where it should be. If we audit on site, maybe it is hard for us to find this problem. But if we assist with the UAV, it is very clear. Disaster mitigation is also important work. For the geological sensitive areas, we are now using the automatic monitoring system. This is the case in Wanfan, and it is a deep slope. Like the other monitoring system, we have the geological investigation and slope stability analysis. But for the monitoring instruments, not only we have the digital and transmission sensor like the rain gauge, theometer, or piezometer, but also we use the new technology to assist this monitor work, which is SAA. SAA is a shape Excel array. It is a 3D animation and moving technology, and now we apply it in the field of engineering. It can capture the real-time deformation data in vertical or in horizontal or in arc. It can automatically scan and record the dynamic data on a specific or on a side point. It can be direct installed into the inclinometer casings, which means it is easy to install. Its length is about 50 centimeters. That allows us to obtain the continuous and more accurate data. And its measurement is reaching to 200 centimeters, which is about 10 times measuring capacity to the conventional instruments. So we are now using this SAA to monitor the slope deformation. This is a structure that we use for automatic monitoring system. We collect data from these instruments and store into the data logger, which is powered by the solar panel. And we transmit the data by 4G module transmission to the data center and the server. And it will automatically generate the email or message to the administrator so that we can real-time monitor the safety of the slope land. This is a real-time and continuous data from our monitoring system. You can see we find that the rainfall and the underground water, the underground water level is strongly relating to the rainfall. And when it rains, the underground water level raises. But for the SAA and the theometer data, we see they are still within the allowable error, which means maybe the slope is still stable. It is hard to find out the slope warning limit or action limit. This is the this is a criteria that we used. It's referred from Dr. Liao's work, but we know it is not that precise when we apply it on every slope. So we try to shift our thinking process. How? From this monitoring system, this is the same deep slope case. We want to find the relationship between the rainfall and the underground water level, how underground water level affects the slope increments, and how the slope increments cause the slope failure. So if we have enough data, then maybe you can build a relationship between the rainfall and the slope failure. So in the future, maybe we can act in advance when we get the weather forecast from the official organization. Maybe we can tell the people who live in the risk area to evacuate. Yeah, we're trying to achieve this goal. And we also put our focus on the man-made slopes. There are a total of 34,000 slopes we have been inspected, and these are investigated by the professional technicians, and all the data were stored into the MSIS system. And we place the identification for each slope, and you query it with GIS map. We rank the man-made slopes into 5 categories. Risk 1 means class 1 means high risk, and this is low risk. There is no high risk man-made slope in Taipei City, but we regularly patrol and monitor the mid-high or mid-level risk man-made slope. When we analyzing the slope stability, the slope unit we need to take into consideration. Man-made slope is a narrow scope view, while the slope unit is a broad scope view. In this case, the slope unit is based on the geographic feature. So in this case, this slope unit, including the 47 man-made slopes, which are under the level of middle risk. With a comprehensive overlook of the slope unit, I think we can catch and predict the slope behavior more accurate. And also we use a new technology that we call point cloud analysis to measure the slope deformation. We have the solar power system, microclimate bars, and creek gauge to collect the environmental and the structure data. And we use the photo. We take the photo and analyze the photo from the retaining wall. We resolve the photo into the points and assign the points the XYZ coordinate and RGB color. When we compare the different time period photo, as long as the coordinate change or the color change, it means the point moves. And with this help, it will help us to find a small displacement or the potential weakness maybe we cannot notice in the beginning. So we still on the way to build this process. I wish maybe someday we will have more result and we can share here. Almost done, sorry. Last part, I will talk about a digital application. The UAV is really a great tool for our slope management. We use the UAV to this case. We use the UAV to create the digital terrain model, and we use the digital terrain model to analysis. And this is a landslide case happened in the Maokong, where located in the Wenshan district. The area of the landslide is about 3,000 square meter. These are the 4 time period aerial photo. Before and after the disaster, after the improvement and the current status. The color means the elevation. If we overlap the aerial photo like this, we overlap the first 2 pictures, then we can understand the spatial distribution of the soil as information for our improvement. If we overlap these 2 photos, then it will help us to know is there any change after our improvement. Like this, since we don't find any obvious color change, then we will feel more comfortable about that the slope is still stable. Because of the advantage of the open data and the high-tech equipment or the digital instruments and the 4G or 5G communication, I think the fundamental environment for the IoT is on the way. So when we united the data with data visualization or artificial intelligence or cloud computing, the intelligence decision supporting system is expectable. This is our prospect. We collect the data, we analyze the data, we store the data into the cloud as an open database, and which will help us as an information for decision support. These are the instruments that can collect data from nature slopes, and these are the instruments collect data from man-made slopes. To summary, we collect the monitoring data, and we store the data into the cloud management platform. We connect with the AI module development. In short term, we want to build the display and alert system, while in long term, we want to achieve the prediction and warning and early warning to ensure the safety of our system, of our citizens. I hope you enjoyed the presentation today. Thank you.
Thanks for the presentation. Okay, now the floor is open for discussion. So we welcome your question or comments. Okay, more than 2 questions.
No question. I have one question about Mr. Lin. The map shows the illegal hotspot map. What's this and how to deal with this?
Sorry, I skipped that part. Okay. This is an illegal hotspot map, which is we analyze the illegal cases, the historical illegal cases. We have many, not too many, but we have the data. We have an illegal case database. So we analyze the illegal cases in the database, and we generate the illegal hotspot map. In this map, it means this area could be the potential illegal development or illegal construction over here. This will help us to plan our patrol routes. So I think because of the big data technology and the business analytics or the tools for the analytics, so I think it is not easy to generate this illegal hotspot map. And also this hotspot map can be adjusted or can be upgraded by the case. If we find there is a new case, then we can put into this database, and then we will control and we will know more about the illegal activity in our slope land. So this will provide us information that we may put more attention on this area.
Can you explain what the difference of the SAA between inclinometer? Yeah.
Okay. I think, like I said, SAA it can automatically scan and record the dynamic data. So it is much like the reflect. You know, you see over here. I think it is a technology that is used in the 3D and animation and movie. But the exact know-how, I don't know the exact know-how. But I think we use this to collect data, like continuous data, and also transfer the data. I think it will has the advantage compared to the traditional inclinometer, and also its max measurement is reached to 200 centimeter. So when the slope failure, it will cause a huge displacement or deformation. For the traditional inclinometer, maybe you cannot collect that kind of data. But from this shape Excel array, we can still track the deformation even though it failure. So I think the failure data is really important for our analysis when we want to find the relationship between the displacement and failure. So I think this would be one of the advantage for this kind of instrument.
Okay, it's time for us to close this session. Thank you for your attention. Okay. We also have gift to presenter.
正在还在努力中，因为其实 data 还不够多。你 IoT 或者是说你要做 big data，一定要资料够多才能够做出那个。IoT 其实已经可以做了，因为现在所有资料都已经自动传输、自动回到我们系统。这我心得。传输不够，讯号不够好。可是我觉得会慢慢好吧。
学长 ，SA 加到园长来了，在楼下。
SA 不是我的业务。
对啊，我知道了，问你一个你不知道的。今年有新版的。